Okay, so this is a linear algebra practice final exam. I'm going to go through this rather quickly. Some of the intermediate steps I'm going to skip through, so you'll have setups and the answers as a reference. Okay, so let's begin. Okay, so we're going to let W equal the following. This X, Y, Z, W, and that is an element of R4. For this, 2x minus y plus 3z minus w equals 0, and x plus 4y minus z plus 2w equals 0. Okay, for part A, prove that w is a subspace of that R4. Okay, so this is a vector spaces and subspaces problem. So for letter A, we could say both equations are homogeneous linear equations. Therefore, W is the solution set of a homogeneous linear system. So it is closed under addition and scalar multiplication. Okay, thus W is a subspace of R4. For part B, find a basis for W. So for the basis, we're going to solve this system here. We're going to let Z equal S. We're going to let W equal T. Going through the computation, solving is going to give us X equals negative 11/9 S plus 2/9 T. Y is 5/9 S minus 5/9 T. So X, Y, Z, W is going to equal S. Negative 11/9, 5/9, 1, comma 0 plus T, 2/9, negative 5/9, 0, 1. And a cleaner basis is obtained by multiplying by 9. So we wind up with negative 11, 5, 9, 0, 2, negative 5, 0, and 9 for that. For letter, so that was, I'm sorry, that was letter B. My apologies, finding a basis for W. Moving along to letter C, determine the dimensions of W. Dimension, well, there's two basis vectors, so dimension of W equals 2. And for letter D, extend your basis for W to a basis for R4. Okay, so one valid extension would be the following. We take the negative 11,590 into negative 509, and then we have a 1, 0, 0, 0, and a 0, 1, 0, 0. As an addendum. Okay, so that's number 1. Again, I'm going to go through this rather quickly. Here's number 2. Okay, number 2. Whoops, I might as well. Sorry about that. Okay, number 2. So define a linear transformation. R3, T from R3 to R3. Okay, so let's see what we could do here. By T of x, y, z equals x plus 2y minus z, 3x minus y plus 4z, 2x plus y plus z. Part A, find the matrix representation of T in the standard basis. Well, for linear transformation problem, for letter A here, the matrix is formed by the coefficients. So A is going to be first row 1, 2, negative 1, second row 3, negative 1, 4, third row 2, 1, 1. Part B, compute the kernel of T. So the kernel we're going to solve for AX equals 0. Set this up as 1, 2, 1, 3, negative 1, 4, 2, 1, 1, and then vertical XYZ equals 0. And then when we perform the computation, the solution is going to be XYZ is equal to T times negative 1, 1, 1. So the kernel of T is the span of that negative 1, 1, 1. Part C, determine whether T is invertible. Well, for invertibility here, since the kernel is non-trivial, T is not 1 to 1, therefore T is not invertible. Part D, what we're going to do is find the image of T and determine its dimension. So the image, first we could determine that the rank is 2, and a basis for the image is given by 2 independent columns. So the image of T spans 1, 3, 2, 2, negative 1, 1. We can take those 2 columns, and then the dimension here of the image of T here is 2. Okay. E, verify the rank nullity theorem. Okay, for rank nullity, dimension kernel T equals 1, dimension image T equals 2. Add them together, 1 plus 2 is 3, so dimension are 3. So rank nullity is verified. Okay, so that's number 2. We can now move along to number 3. Okay, so number 3. Okay, we're given the matrix here A. Compute the determinant for letter A. So performing the mathematics there, computation, determinants, and matrix structure problem. If you compute the determinant, row reduction or cofactor expansion gives a determinant of A as -6. Okay, so I left out the intermediary steps there. For part B, determine whether A is singular. Well, since the determinant is not equal to 0, A is non-singular. Part C, using the cofactor expansion, compute the 2, 3 cofactor. So here, when we do this, following setup, we're going to delete row 2 and column 3. It's going to give us 1, 2, -1, 0, -2, 1, 2, 0, 3. Determinant is -6, so that's C sub 2, 3. That's -1 to the 5th times -6. So we're going to get a +6 for that cofactor. Sorry. Part D, find the determinant of the following. Sorry about that. That B equals 2A transpose inverse A without explicitly computing the inverse of A. Okay, so this is an interesting one. So since A here is 4 by 4, we could say that the determinant of A of 2A transpose inverse A, that's going to equal 2 to the 4th determinant of A transpose determinant of A inverse. So the determinant of A transpose, that's going to equal the determinant of A, and the determinant of A inverse is 1 over the determinant of A. So the determinant of B is going to be, that's 16 determinant of A times 1 over determinant of A. And the determinant of B is going to just be 16. Okay, so that's A, B, C, D for number 3. We're ready for number 4. Okay, so for number 4 here, okay, we're given a matrix 4, 1, 0, 1, 4, 0, 0, 0, 2 for the respective rows. Part A, find the characteristic polynomial of A. So this is eigenvalues and diagonalization problem. So to get the characteristic polynomial, we're going to set this up determinant of that A minus lambda I and set this up 4 minus lambda, 1, 0, 1, 4 minus lambda, 0, 0, 0, 2 minus lambda. So P of lambda is going to equal parentheses quantity 4 minus lambda squared minus 1 times quantity 2 minus lambda. 4 minus lambda squared minus 1, that's going to give us 5 minus lambda, 3 minus lambda. So P of lambda equals 5 minus lambda times the quantity 3 minus lambda times the quantity 2 minus lambda. And that's a segue into letter B. Letter B, determine all eigenvalues and eigenvectors. So the eigenvalues and eigenvectors are going to be lambda equals 5, 3, and 2. And for each now, for lambda equals 5, the span is 1, 1, 0. For lambda equals 3, the span is -1, 1, 0. And for lambda equals 2, the span is 0, 0, 1. Okay. Part C, determine whether A is diagonalizable. Okay, so for part C here, there are 3 distinct eigenvalues, so A is diagonalizable. Sorry. Part D, that was part C. Now for part D, if diagonalizable, find matrices P and D such that A equals P, D, inverse A. Okay, so for part D here, we're going to use the eigenvectors as columns. So we're going to set P equal to row 1, -1, 0, 1, 1, 0, 0, 0, 1, D, 5, 0, 0, 0, 3, 0, 0, 0, 2 for the rows. And A is going to wind up as P, D, inverse P. Okay. And letter D, compute A5 using diagonalization. So A5 or A to the 5th, some people call it A5, some people A to the 5th, equals PD to the 5th, P to the -1 or inverse. So d to the 5, that's going to wind up 3125. When we do the computation, 312500, 02430, 0032. And so a to 5 is going to equal 1684, 1441, 0 for the first row, 1441, 1684, 0 for the second, and 0032 for the third when we perform the computation. So that's number 4. And let's move along to number 5. Okay, so number 5, consider the vectors v sub 1, 1, 1, 0, 1, v sub 2, 2, 0, 1, negative 1, and v sub 3, 1, 2, negative 1, 0. And we're going to apply the Gram-Schmidt process to obtain the orthonormal basis for the span v sub 1, v sub 2, v sub 3. Okay, so orthogonality and inner products here. So for part A, we apply Gram-Schmidt. So we're going to let u sub 1 equal v sub 1 equal 1, 1, 0, 1. And then we have the norm of u1 that comes out to root 3. So e sub 1 is going to be 1 over root 3, 1, 1, 0, 1. And u sub 2 is going to equal v sub 2 minus that projection that we have, the projection of v2 onto v1, onto v2 onto u1 there, rather. So we take the dot product here, v sub 2 dotted with u1 equals 1, and then the dot of u sub 1 dotted with u sub 1, that equals 3. U sub 2 equals v sub 2 minus 1/3 u sub 1, or u1. Some people just call it u1, then u sub 1 interchangeably. Depends on how you prefer it. Or u sub 2 now equals that v sub 2 minus 1/3 u sub 1. So u sub 2 is 5/3, negative 1/3, 1, negative 4/3. And what we could do now is we could clean this up by multiplying by 3. So we could use u sub 2 equals now 5, negative 1, 3, negative 4. Going up here, we calculate its norm. The norm of that u sub 2 is going to be 25 plus 1 plus 9 plus 16, the square root of 51. So e sub 2 is 1 over square root of 50. 1 times 5 times negative 1 times 3 times negative 4. So u sub 3 is equal to v sub 3 minus that projection here, and minus the other projection. This simplifies to a vector proportional to u sub 3, 0, 1, negative 1, negative 1. And its norm is also root 3. So e sub 3 equals 1 over root 3, 0, 1, negative 1, negative 1. So therefore, an orthonormal basis is the following: 1 over root 3, 1, 1, 0, 1, comma, 1 over root 51, 5, negative 1, 3, negative 4, comma, 1 over root 3, 0, 1, negative 1, negative 1. Okay, moving on to letter B. Find the orthogonal projection of u equals 3, 1, 2, 0, and onto span v sub 1, v sub 2, v sub 3. Okay. So using the orthogonal vectors from Gram-Schmidt, we could say this projection here of that we're given, it's going to be this summation I equals 1 to 3 u dot u sub I over u sub I dot u sub I u sub I. And the results of this projection are going to be 50 when you do the computation: 56 over 17, 31 over 51, 77 over 51, 5 over 51. Okay, sorry about that, 77. And for letter C, compute the distance from u to the subspace. Okay, well, when we do that, computing this distance, it's going to equal negative 5/17 here, 20 over 51, 25 over 51, negative 5 over 51. So D, comma, U, S, that's going to be that norm here of this U minus the projection. So that when we do the computation, it's going to be 5 root 51 over 51. Okay, so that's it for ABC there. We're ready for number 6. That was number 5. Okay, so here consider the following. We have a systems of differential equations here. We have this x prime of t as axt, and A is given as 3, negative 1, 1, 1 for the respective rows. Part A, find the eigenvalues of A. So systems of differential equations. So that A, the eigenvalues, get the determinant first, set it up, perform the computation. We wind up with our eigenvalue has a algebraic multiplicity of 2, and our lambda equals 2. For part B, find the corresponding eigenvectors. Well, the eigenvectors, we're going to solve for A minus 2i times v equals 0. A minus 2i equals this row, this what we have here, 1, negative 1. Second row, 1, negative 1. So we could set this up as x minus y equals 0. So v is 1, 1. So the span is just 1, 1. Okay. C, determine the general solution of the system. General solution, there's only one eigenvector. So we need a generalized eigenvector q satisfying A minus 2i. That quantity, q equals v. We'll choose q equals 1, 0. And then we're going to get this A minus 2i times q equals 1, 1 equals v. So our x of t is going to equal the following. X of t equals e to the 2t, bracket c sub 1, column 1, 1 plus c sub 2, parentheses t, column 1, 1 plus column 1, 0, close parentheses, close bracket. And for part D, solve the initial value problem that x of 0 equals column 2, negative 1. So initial condition x of 0, okay, is going to equal c sub 1, column 1, 1 plus c sub 2, column 1, 0 equals column 2, negative 1. This is going to give c sub 1 plus c sub 2 equals 2. So c sub 1 equals negative 1, c sub 2 equals 3. Performing the computation. And so we're going to get x of t equals e to the 2t, and then the column is 3t plus 2, 3t minus 1. Okay, so that's all for number 6. Moving along to number 7. Okay, so we let b equal the following: 1, 0, 1, 0, 1, 1, 1, 1, 0. Be a basis for R3. Part A, find the change of coordinates matrix from B coordinates to standard coordinates. So a change of basis problem. So the matrix from the B coordinates to be standard coordinates has basis vector as columns. So we just rewrite this as row 1, 0, 1, 0, 1, 1, 1, 1, 0. Okay. Part B, find the coordinate vector of v equals 2, 3, 1 relative to b. Okay, so we have the coordinates v equals 2, 3, 1. We want to solve this p sub v, this p sub b times v coordinate b equals v. So set this up 1, 0, 1, 0, 1, 1, 1, 1, 0 for our rows, times column ABC equals column 2, 3, 1. So a plus c equals 2, b plus c equals 3, a plus b equals 1. So we have for this solving a equals 0, b equals 1, and c equals 2. So we get this v sub b is column 0, 1, 2. Okay? Alrighty. Letter C, we let w sub b equal this column 1, negative 2, 3. Find w in standard coordinates. So what we do here, we take that w and we take 1 times 1, 0, 1 minus 2 times 0, 1, 1 plus 3 times 1, 1, 0. Simplifying this, and w equals 4, 1, negative 1. Okay, so that's number 7. Moving along to number 8. Okay, number 8, symmetric matrices and quadratic forms. So we're going to let q, x, y, z equal 4x squared plus 4xy plus 2y squared plus 2xz minus 2yz plus 3z squared. Part A, find the symmetric matrix associated with q. So symmetric matrices and quadratic forms problem. We have a symmetric matrix for letter A. The matrix has diagonal entries from squared terms and half the mixed coefficients off diagonal. So our A is going to be 4, 2. So our respective rows here for A, 4, 2, 1, 2, 2, negative 1, 1, negative 1, 3. So Q of XYZ is going to be row XYZ, A, column XYZ. All right. For part B, determine whether the quadratic form is positive definite, negative definite, or indefinite. Okay, so for definiteness, use leading principal minors. So we have that delta sub 1 equals 4, and that's greater than 0. And that delta sub 2 equals this determinant 8 minus 4, which is 4, that's greater than 0. And delta sub 3, the delta symbol sub 3 equals the determinant of A equals 2, greater than 0. Okay, so since all leading principal minors are positive, Q is positive definite. Okay. Part C, diagonalize the quadratic form by an orthogonal transformation. So for letter C, the orthogonal diagonalization. Since A is real symmetric, it is orthogonally diagonalizable. Okay, A equals that PDP transpose. The characteristic polynomial is going to be lambda cubed minus 9 lambda squared plus 20 lambda minus 2 equals 0. We're going to get approximations here. It's important to say that these aren't exact eigenvalues. The eigenvalues are approximately lambda sub 1 is about 0.1049, lambda sub 2 is about 3.6027, lambda sub 3 is about 5.2924. So in orthogonal coordinates, it's going to be Q is about 0.1049 u sub 1 squared plus 3.6027 u sub 2 squared plus 5.2924 u sub 3 squared. Okay, and letter D, classify the geometry of the surface Q of XYZ equals 0. So what's going to happen here, geometry here, because all eigenvalues are positive, Q of XYZ equals 1, that happens to be an ellipsoid. So the surface of this is an ellipsoid, and that's all for number 8. Let's move along to number 9. So number 8 was symmetric matrices and quadratic forms. Number 9. Okay, so number 9. So here, let A equal this matrix row 510, 051, 005. So find the characteristic polynomial for letter A. Okay, so this is Jordan form and nilpotent matrices. So for letter A, characteristic polynomial, since A is upper triangular, its eigenvalues are the diagonal entries. So P of lambda equals 5 minus lambda cubed. Also equivalently, P of lambda equals negative quantity lambda minus 5 cubed. Sorry about that. B, determine the algebraic and geometric multiplicities of the eigenvalue. So part B, algebraic and geometric multiplicities. So the eigenvalue is lambda equals 5. Its algebraic multiplicity is 3. So A minus 5i equals this matrix here, 0, 1, 0, 0, 0, 1, 0, 0, 0. Solving quantity A minus 5i v equals 0 gives y equals 0, z equals 0. So the eigenvectors have this form, v equals x, comma 0, comma 0. Geometric multiplicity happens to be 1, so the eigenspace is one-dimensional. Part C, determine whether A is diagonalizable. Well, since geometric multiplicity 1 does not equal 3, A is not diagonalizable. For part D, find the Jordan canonical form of A. Part D, the Jordan form, the matrix is already a single Jordan block. J equals 510, 051, 005 for the rows. And for part E, compute e to the AT. Well, we write A equals 5i plus n, where n equals this 0, 1, 0, 0, 0, 1, 0, 0, 0 matrix. Since n cubed is 0, we're going to set e to the AT equal to e to the 5t, e to the nt. And e to the nt is just going to be I plus tn plus t squared over 2 n squared. So e to the AT equals e to the 5t times this quantity, rows 1t, t squared over 2, 0, 1t, and 0, 0, 1. Okay, so that's all for number 9. And now we go to number 10. Okay. Whoops, sorry. So number 10, so we have let A equal this, column 1, 1, 0, 0, 1, 1. B equals this column 2, 1, 3. So form the normal equations for the least squares problem. A x hat is approximating B. So this is a singular value decomposition and least squares problem. Part A, the normal equations are A transpose A x hat equals A transpose B. So A transpose A equals row 2, 1, row 1, 2, and then comma here, A transpose B equals 3, 4. Normal equations, row 2, 1, row 1, 2, x hat equals column 3, 4. Okay, letter B, find the least squares. Least squares solution, we're going to solve this system. 2x plus y equals 3, x plus 2y equals 4. Okay, performing the computation here in the algebra, we're going to get x equals 2/3 if we solve by substitution, and y is going to equal 5/3 here. So our x hat is the column 2/3, 5/3. For part C, compute the residual vector. The residual vector is r equals b minus a x hat. Ax hat equals 2/3, equals this column 2/3, then 2/3 plus 5/3, 5/3, which becomes column 2/3, 7/3, 5/3. And now to compute r, we take 2, 1, 3 minus this column 2/3, sorry about that, 7/3, 5/3. And when we subtract that from this piece, we get 4/3, negative 4/3, 4/3. So our r residual vector is 4/3, negative 4/3, 4/3. Letter D, find the singular values of A. Well, the singular values are square roots of the eigenvalues A transpose A. So A transpose A is this row 2, 1, this row 1, 2. Its eigenvalues are 3 and 1. So its singular values are root 3, square root of 3, and 1. Part E, determine the rank and nullity of A. Well, the rank and nullity, the columns of A are independent, so rank of A is 2. And since A has 2 columns, the nullity A, 2 minus 2 equals 0, so nullity of A equals 0. Okay, so that's all for number 10, and then we go to number 11. Okay, so number 11, more of an extra problem here. Okay, sorry, this is if there was some abstract algebra in the course or not. So this is extra. So abstract linear algebra problem, extra. So we're going to let V equal the following. Okay, and the vector space of real polynomials of degree at most 3. And we're going to define this T. Okay, so T from P3 of R to P4 of R. Well, actually from here, I'm sorry, T of P3 of R to P3 of R by T of P of X equals P prime of X plus XP of X. So if we define it as this from P3 of R to P3 of R, we want to identify the issue here. Okay, so this abstract linear algebra application, so if P of X, okay, all right, if it's an element of P sub 3 of R, then X, P of X may have degree 4. So for example, P of X equals X cubed gives X, P of X equals X to the 4th. So an issue is T of P may not lie in P sub 3 of R. So therefore, as it's written originally, this is not well defined. A corrected version would be either T, right, from P3 of R to P4 of R, or define T by projecting away from the X to the 4th term. All right, so that's all for this. I just went over this rather quickly so you have it as a reference. Hopefully it could be used as extra practice for your linear algebra or just for fun. Okay, thank you very much, and have a great day.